Hey ladies and gents, let's do another little experiment with the refractive index. Now, as we all know, glass is transparent. Light goes right through it, and we can see it right here with our two glass beakers from lab. Now the thing is, glass is transparent, but we can still see a very visible edge to the glass, and that's due to the difference in refractive index between the glass and the surrounding air. That difference in refractive index essentially allows us to see the edge of a transparent structure or substance like glass. Now, if we place our smaller beaker into our larger beaker, James, if you wouldn't mind doing that for me. Let's put it right down the bottom, bud. Excellent. You notice we can still see our smaller beaker, even though the two beakers have the same refractive index because they're made of the same type of glass. You got to realize that the light is still slowing down as it passes between the different media. So as the light hits the back of the first glass, travels through the air, it bends in a little bit, and then as it hits the smaller beaker, it bends a little bit more. As it passes through the smaller beaker, it bends some more again. And so each time the light passes through the different substance, as we remember, it bends a little bit. And that way we can see the edges of both glasses, even though the two glasses have about the same refractive index. Now what we're talking about with the Beck line, where we're doing refractive index analysis on glass fragments, is that we're trying to essentially get that edge to disappear, or that halo, as it's called in the microscope. So let's see if we can try to make the edge of the smaller beaker disappear inside the larger beaker by adding something with a little bit of a higher refractive index than air. Let's try water this time. All right, and what we can see is, yes, there's a bit difference. But we can still see the edge of the glass pretty well. Due to the higher refractive index of water, it tends to bend the light a little bit more, but we can still see, if we zoom in nice and close, the edge of the glass beaker inside the larger one. So obviously, there's still too big of a difference with refractive index to get that edge to disappear completely. Let's try it with something with an even higher refractive index. I mixed up some optical oil earlier today, and this optical oil is made of a mixture of mineral oil and vegetable oil. Now, I'm not sure if this is perfect, but I think it would probably have a little bit of a higher refractive index than at least the water. So James, why don't you give it a pour? Very good. And as you can see, the edge of the glass has essentially disappeared. You can see a little bit of an edge with the gradations from the graduated cylinder, but still, if you didn't see the mark in the gradations, you really wouldn't see the edge of the glass all that well. So you can see that's essentially what we're trying to do with our refractometer. We're trying to adjust the refractive index of our media, usually an oil of some sort, not too dissimilar from our optical oil. And by adjusting its temperature, it adjusts the refractive index of the oil. It has a specific refractive index at a specific temperature. And when we hit the right refractive index, the edge of the glass fragment suspended in the oil will essentially disappear. Not too shabby.